then I'll also do this story here. We'll record this. All right, so I'm making like 3 different recordings. One of them will work. Okay, so welcome. Oh, here we go, Paul. You're on. He's live. Good to see you.
Sir, there's a couple others in the Google Meet right now, so I'm going to hop back into that and send them over here.
Oh, there's a Google Meet still hanging out? Oh, my. Okay. Let me update the calendar. I was trying to figure out which one to use, and I really don't have a preference, but people seem to think Zoom was cool, so I switched it to the last minute. Oh, I see. Yeah, let me edit this and destroy the Google Meet.
We were all hanging out in there waiting for you, and they're a bit confused about where everybody was.
Davis, all right, good. Okay, this is much better. I was kind of stalling here, hoping that my class would show up. Okay, great. And then John Thomas. Oh yeah, okay, Jack. Okay, got it. Okay, we're all here. Excellent. All right then. Welcome. Our class leader is Maria. Is maybe you didn't hear that, but congratulate her when you see her. And I will be teaching remotely until, if anything changes, I'd love to come in. But with the childcare situation, I kind of got to stay here. So I think the class size is small enough that we can probably all fit in the classroom if and when that happens. But I guess we'll just stay tuned and agile, etc. Oh boy, Mitch just crashed. Great. Well, that's fine. So let me go ahead and the classroom, that's going to be our main kind of learning management system here. Maybe I'll share this. Here we go. So you should be able to see under classwork. I'm not sure how familiar you are with Google Classroom. Is everybody use this kind of over the summer, I'm hoping? Okay, I know I had to do it with my child for the rest of his school year, and it was a mess. So there's probably different ways to set it up. I'm looking into the coursework tab. I just put admin up here, so that's the Zoom link, the syllabus, the course policy. We'll go over those documents. All of the lectures here, my intention is to put the PDF document as well as the recording once that's done. Sorry, I'll try to do a clean recording where it's much quicker without the questions and interaction, and that way when you want to go back, you don't have to watch an hour's worth of video to see some content. So these, you'll just expand them out and you see the PDF of the lecture. These lectures are, I'm trying to keep them short, so they're each about 7 slides. My goal is about maybe 15 minutes per quote lecture. And that way they are kind of digestible chunks, and you can go back and find stuff rather than sort through an hour's worth of me just going on and on. So we'll certainly do lecture 1 today. We'll try to do lecture 2 and see how far we get. If not, if we don't get to 3 now, we'll do it in lab tomorrow. So assignments here have a slightly different icon, and this is your first one getting started. It's just install the software. I've given you some screenshots here as well as a video that walks you through the steps. So we'll do it together in lab, but as internet comes in and out or the screen's blurry, don't panic if you miss something. My intention is for it all to be recorded so that you can access it on your own. Any questions about the classroom? Awesome. Okay, so let me switch over then to lecture 1 here. If you want to follow along in your in the PDF or use Zoom, however you want to do it, but we'll switch to lecture 1. And let me start to present that. Okay, so can you all see, let's see, Maria, can you give me a verbal yes if you can see the screen? I can no longer see you guys since it's all in presentation mode here.
Yes, sir, we can.
Very good. Okay, so here's the overview of this lecture. I'll just tell you a little bit about myself, background, how well I handle remote learning, the syllabus and the policy, of course, and we've already talked about Google Classroom, so that'll be fine. The biggest part of this slide deck is the software slide. That's all the links to download everything. And I would encourage you to get started on that as soon as you can. Some of these downloads take a little while, and especially if the internet's hit or miss, start early. Okay, so about me, I got my undergraduate degree from Princeton in electrical engineering. While I was there, I did ROTC in the Army. So when I graduated, I went to Fort Bragg, was a platoon leader there, and then deployed to Camp Liberty, Iraq for a year, where I helped install large-scale network operations. And then I got out of the Army, grew my hair out, and went up to MIT, where I got my master's and my PhD in electrical engineering. So while I was there, I worked a lot with large machinery, like maintenance and condition tracking of large power plants and machinery, and that happens to be exactly what's on ships. So while I was there, I ended up doing more with the Navy than I ever expected, and ultimately ended up here. So I do have an Army background, but I gotta say your duty stations, and in particularly Annapolis, beat anything I ever saw in the Army. So go Navy and go Army. But there's my background, and I'm happy to talk more about any of those pieces if you're interested in EI or whatever. Okay, so outside of the classroom, I do a lot of research. And this is just a snapshot of a few of the projects. So this is, on the left is the Gilliland, which is a very large resupply ship and storage vessel for basically a division of Army trucks. So this is like 5-story parking garage, essentially located outside of Baltimore. And the goal with this project is to put a few sensors on the main power generation equipment, and then be able to see everything that's happening on the ship. So we'll be able to find like faults in the air handlers, faults in the chillers and compressors, and do that all just from a couple sensors. So that's out there in Baltimore. This is a Coast Guard ship with some graduate students who I co-advise at MIT, as well as some Coast Guard officers. This on the right is a YP. So if you ever end up on the YPs this year, YP 708 has a 3D printer that I've got installed on there to try to do long-term benchmarking of sort of environmental hazards for AM on Navy ships. There's a big push to be able to 3D print repair parts underway. And then this is my office used to be in Maury. Now we're over in Hopper. And now that's actually all in my basement, so I can show you that in a bit. But we try to maintain a pretty active research program here. If you're interested in participating in any of this stuff or learning more, please don't hesitate to reach out. All right, so remote learning. You've already got this set up. This is based on guidance we get from the administration side to have your videos on, unless there's some kind of bandwidth constraint where that becomes untenable. So for now, it seems fine. Please keep your videos on. Microphones, I don't mind if they're on or off, although it seems that with a lot of simultaneous learning in the Bancroft rooms, probably microphone off is a good idea. But I will not be checking the chats, just the way my screens are set up. So if you have a question, please unmute yourself and go and ask, just like if we're in class. Like I mentioned, I'm going to make an effort to record all these classes, so if there is a glitch in the internet or you had to get up and run to the head, don't worry, you should be able to get all the information. And everything will be posted to Google Classroom. So this is what I'm up against here. I have 3 small children, and this was the remote learning system last year in the spring. So that's a Amazon Prime desk box with Google Classroom open there. And so there's plenty of chaos on my end. I appreciate your flexibility as we go forward. If you have technical or personal issues or anything that is hampering your ability to learn here, please let me know and we'll adjust and make it work as much as we can. Any questions so far? All right, Maria, are we still there?
Yes, sir, we're still here.
Okay, good. All right, so here's the big reveal that you signed up for a class that I'm actually not teaching this semester. So EW430 by design is supposed to be microcontrollers, and we're building up from the ground, with the starting with transistors, building all the way up to a functional piece of hardware at the end of the semester. And then in the spring, if you took 432, we would move up towards Linux and Python, and we kind of keep building. Since I can't really give you hardware to work with right now, we're going to flip-flop and do the spring semester in the fall. Hopefully that doesn't cause too much heartache. If you are passionate about the microcontrollers and would like to explore that area, I'm happy to give you a kit and to point you in the right direction. It's just, logistically speaking, it's pretty hard to debug that stuff and to be there with you. Or without being able to be there with you, I think it's better that we try to do something software-based. So to that end, here's the structure so far. I have it all the way out to 16 weeks. This slide is just made up, right? I don't know what's going to happen. So I think we can count on the first few weeks being under our control, and we'll just see where we go. The class is going to be based on the Python programming language. That's a new language to you, I imagine. So we'll spend the first chunk of the course learning that. And then today I hope to motivate kind of why we're using Python versus some of the language you already know. The labs will be progressive. Each one will build off the previous one, and our goal is to build a pretty complicated computer game, Battleship, that you can actually play over the internet with another person, and detect if they're cheating, and have graphics and all sorts of cool stuff. So this is designed to reinforce the programming kind of language of Python, as well as how to build and structure larger projects, because a lot of what you've done to date, at least in our coursework, has been very small, single-purpose built programs like, hey, I need to read a sensor and burp it into MATLAB. So how do you actually build a larger program and manage it and the complexity that comes with that? After you've mastered Battleship, that'll kind of segue us into computer networks, because we'll need to do some basic networking to connect your Battleship games to each other. And so the second portion of the course is entirely about the web. And we'll be kind of working again from the ground up the idea of, hey, we've got the ability to connect two computers together. I can send ones and zeros across. How do I actually turn that into the internet, into a web page that you know and love? So we'll be talking about the structure of web documents, and you'll be building up a version of like a message board, so that you can post comments to your message board and people can like your messages, and there'll be a ranking system so the best messages will bubble to the top. And so I think it will be a pretty cool product at the end. And all things going well, the goal is then in the spring we would flip-flop back to microcontrollers, and at the end of that, the full year of instruction, you should be able to see messages that have been posted to your website pop up actually on the physical piece of hardware you build. And that would kind of connect everything together, right? This Internet of Things that you can build hardware and control it from wherever you are in the world. So the two courses are linked. They're not in their prerequisites because of that. So that's kind of the very broad view of my goals of the class, and sort of a justification on why the two are flipped. Neither semester requires the other. It's just nice if you know both, because then you see the whole picture. Questions on the syllabus? All right. Let's see. Just to pick on someone else, Davis. Are we still any questions?
Not at the moment, sir.
Okay. Anybody like desperately upset about the microcontrollers? That we can still change your class and move you around. I think, for you being a selfish perspective, saying, hey, I wanted something for my capstone, or I need to know this stuff. I imagine this, by flipping it, it's actually more useful to you. The topics we cover this semester will probably be more applicable to your capstone projects than the low-level hardware. So that might be a benefit. If you do have a problem, please send me an email and we'll work it all out. This is just something we kind of came up with over the summer, and I hope it works out for you all. I'm excited. And you'll notice a big chunk of the last piece of the class is student topics. As firsties, you've seen a lot in your other classes, and hopefully you have captions that are interesting to you, or have personal questions like, man, I really wish I knew more about Bitcoin, or how does Google Docs work, and with all this synchronous editing. And so if there's any kind of topic that's even tangentially related to the course of study here, I'd be happy to consider it and add in some lectures. And my goal for this is for it to be a chance to wrap up and tie up any loose ends that might have been ignored in previous classes. I teach 200, and a lot of that is like, hey, we're not really going to explain this. It's kind of a black box. Trust us. We just need to move on. And in this class, if any of that, you say, what is in that box? I'm happy to tell you. So please think about your questions as we go through this course, and let me know. I would love to adapt the course to meet with the topics you're interested in. Okay. Still going here. Course policy. Please review it. It's a PDF in that Google Classroom. From lecturing the course policy every, we were supposed to do it the first day. Everyone goes to sleep until I say grading. How is it done? And then everyone, looks up quickly and then goes back down. So let me just extract out that portion. We're going to have 2 1-hour exams. Those are the 6 weeks and the 12 weeks, and then a final. Pretty standard. And then the lab exercises are account for the rest of your grade. So there's no separate homework for this class. The labs are intended to be started during the lab period, and then completing it will be your homework for the week. If they work, you'll get 100% for that week, and if they don't work, you'll get partial credit as, we can figure it out. There's no lab write-up. There's nothing except show me that it works, which is going to be hard enough. As you're trying to figure out your grades and what you need to do, just be aware that all labs must be done. So even if you figure out that the percentages work out where if I forget lab 3, don't worry about it. That's not going to be possible, right? Because these labs build on each other, you really need to have each one done in order to progress to the next stage. So just to make that clear in terms of grading, if you fail to turn in a lab completely, say, hey, I just didn't do lab 4, then that's going to be a 1-letter grade deduction. All right. I think that's pretty good. Collaboration, I'll mention a little bit later. Questions on the grading? Okay, so if it works, 100%. If it doesn't work, we'll figure it out from there. And then I'm not going to put out a late policy right now. I just want to see kind of how things go in the past, and what I expect to do, but I'm going to kind of wait a week. Is say it's 10% per day. So if labs are each 10 points each, if you turn in the day of, it's full 10. If you turn in the next day, it's going to be 9, 8, 7, etc. All right. I will also post solutions to the labs as well. Okay, for EI, please email me and we can just set up a Google Meet or a Zoom, whichever you feel comfortable with. Of course, we can't do in-person EI, so that's unfortunate. Okay, so let's say that's the course policy. Collaboration. So work together. I mean, as COVID permits. You may get assistance from others, but do not copy their code. I don't want to see something like lines 20 through 40 are from Greg. Thanks, Greg. No, you could say, I worked with Greg, we struggled through this, and we both ended up writing it ourselves. But if you do work closely with someone, please annotate that in the comments of your code just to make me realize it's not some kind of questionable piece if the code looks similar. But you absolutely may not copy their work. And it's too easy to test. You have digital code here. It's easy to digitally compare. So please don't do anything there that involves copying. But otherwise, please work together. Every year I've taught this. Essentially, everyone seems to come with the solution at the same time, and I hope that's because they're all working together. One other thing for the course policy: exams will be in open resources. That is particularly useful now that. I can't really monitor your resource usage anyway, but I do that every year. I don't like the criticism I had it as a student where like, hey, why do I have to memorize this stuff? If I was really doing it, I just Google it. So my response to that is, well, then Google it. I think you'll find the exams challenging still. I always get the feedback that they are hard exams, but you don't need to worry about memorizing a bunch of stuff or making a bunch of notes on a cheat sheet or something. You may use the internet, you may use your programs, the videos from the recorded lectures, anything you can find except other people. So don't post a question to a forum or don't get into Google Meet with a peer, but anything else is fair game. All right, so textbooks, I'm not going to be, we'll be starting, it will certainly work through the first few chapters of the Python book. That's going to be the Hangman video game, and you'll see how that works. So you will need access to this book. It is online, so you can go to this URL, and he's got it all set up, which is nice. I find that it's a lot easier to work with a paper copy sometimes, so I've got my screen in one thing and got the book in the other, and it's not an expensive text, so I recommend that you purchase it. I will also put out a few other resources, so if you want to different structure and folks, if another Python book is more up your alley, my goal is for you to learn Python. How you learn it, I don't really mind. So we will be using this book. It's online, but if there's another book that you prefer to purchase, I will send out an email later that has some other recommended text. We will be using Linux later in the semester. It won't be a big portion of the course. You'll need to know how to do a few things in Linux. But if you're interested in using Linux at a lower level and really understanding how it works, I would recommend getting this book, How Linux Works. So I won't be referencing this book beyond this slide, but I do recommend it as a text. Sometimes figuring out where to start with Linux can be a bit daunting. So if you're a person who likes books, this is a good one. Questions? Greg, any questions?
No, sir.
All right. It's just me here staring at this, my own PowerPoint slides that I created a few days ago. So every now and then I got to make sure that somebody's on the back end. I appreciate it. Okay, so here's the big slide. This is the one that I want you all to be able to open up and click on these links. You'll need Python 3.7. That is the Python program that allows you to run Python. And it's important you get 3.7. So 3.8 is the latest release, but Pygame, which is the video game engine we'll be using in the course, does not support 3.8 yet. So please get the 3.7 version. I think that link sends you directly there. If you go to the Python page, just make sure you're getting the right thing. There are several different flavors, depending on your hardware platform. You should get the AMD 64 version. So that means that you have a 64-bit laptop you're running it on that basically has an Intel architecture. So get the AMD 64. Also, you'll need PyCharm, and when you go to this site, you'll see there's a community edition as well as a professional edition. We will be using some of the features in the professional version for our website. It just makes it a little bit easier to debug and run our code. The community version is totally functional, and going on after this course, if you want to continue to use PyCharm or continue to work on Python, PyCharm is totally free, and all the major features of it are available in the community edition. But there are just a couple buttons we need for the second part of the course. So please, when you install this, get the professional version, which is free with your USNA email address. You're going to need PuTTY as well. That's going to allow, we're not going to need this again until later in the semester, but this is a tool that allows us to connect to remote servers. Again, get the 64-bit edition. GitHub Desktop, Get, these are tools for version control. Like I said, one of the big parts of this course is how do you manage larger software projects beyond just, hey, I have main.c or a MATLAB script. And that the tool we're going to use for that is Get. So please download those two pieces. And then finally, Wireshark is a tool that allows us to inspect network traffic, and we'll find that useful once we start to talk about computer networks. Wireshark does fall into a more of a gray area in terms of the kind of software that might be used for nefarious purposes. It's purely a monitoring tool. You can't use it to inject, bad data onto a network or anything like that. But if you're Googling around for tips on how to use Wireshark and seeing those kind of forums, all manners of people use Wireshark, and just be responsible and careful on what you try to do. We will be looking at computer security in this course. I'm not going to show you any live exploits. In terms of like they could be weaponized, but we will talk about vulnerabilities, and when I do, I'll make it clear what is acceptable use and what's not. But Wireshark is totally fine. You can't get in trouble for using it. But if you poke around and find, you might be interested in Nmap and you go, don't run Nmap on the USNA network. So there's a kind of a vague disclaimer there. Again, get the 64-bit edition. We won't be using Wireshark or PuTTY until later in the semester, though. All right, there's the Google Classroom. Actually, we kind of inverted the order of things. We talked about that first. Add the calendar from the class to easily track when we meet and when the assignments are due. I apologize for that Google Meet link. Last night I was trying to decide which, Zoom or Google Meets, which one to use, and we'll be using Zoom until we decide not to use Zoom. If one of if you all have a preference, please email me and let me know. I'm really agnostic to it, but Zoom does have some features like breakout rooms and that seem to be nice. So use Google Calendar. It'll add on the assignments. It'll give you the class meeting links and stuff like that. Okay, that's the end of lecture 1. How are we doing? Questions? Maybe like one question. Just, for fun.
So the link for the PuTTY, when I tried to use it just goes to like a 404 error.
Ah, okay, that's good to know.
You can Google it and find a little download that way too.
Yeah, those are just links that are meant to help you out. I guess that's my fault. These links are from last year, so maybe he's moved PuTTY around. But PuTTY is actually available on Software Center as well. So if you have Software Center on your laptops, I'm not sure how that works for your view. Sometimes I see different pieces on Software Center. But just Google PuTTY and download the 64-bit installer. I'll talk more about PuTTY when we need it, but thanks. Good question. Anything else? Okay. Yeah, so I guess just to show you where I'm at, this is my bench here where we'll, if there's any need for hardware, we'll be talking about it there. And then, I've got, my recreational area as well. So this is my little, my bunker. So this is where I'll be. And if you have any need for hardware help as you work on capstones, I'm oftentimes asked to kind of consult on some of these projects. So if there's any need for that, please let me know. I also have a Davis, you're there, right? Yeah, he's controlling a 3D printer behind that door behind me over a series of remote connections. So all about internet connectivity and building large distributed programs here. So hopefully we'll have some fun, and I'm looking forward to this. Last chance for lecture 1. This is going to be gone. It's never going to come back. Money's coming in and out. Okay. Can we do lecture 2? Can we start lecture 2? What do we think? Okay, let's do it. Maria's got kind of a nod, like it's a half nod. Okay. Because we want to do some content on the first day, right? It's no fun if we just talk about course policies. Let's see here. Okay. All right, so Davis, can we see that you see 430 operating systems?
Yes, sir.
Very good, full screen. Awesome. Okay, so this course is going to be, and again, pretend like you had the fall already where we talked about microcontrollers. We're going to be moving up the stack away from bits of hardware like the embed and on to actually writing a program that runs on your computer. And so that's a big kind of mental model, a difference in how programs work and how they run together. And I want to emphasize that before we go any further. So think back then to 200, which is the last time I know you worked on these things. I'm sure you've done them in the past. But this is the standard model of how you write code, right? So we're going to write some C code on the right-hand side of the screen here, just to blink a light, right? So we're going to include a library, embed.h, declare our resource, LED1, and then just go in a loop, right? And it's really important here to understand, right? This, what does this while one mean? Forever, right? While true and one is true, do this. And so we're going to set the LED on. We're going to wait a bit, turn it off, wait a bit, and turn it back on. Okay, and so this simple little program here is never going to stop. And I never wanted to stop, right? The intention of purpose-built hardware like this is to do a job, do it well, and do it forever. So once I'm happy with this code, I'm going to run it through a tool called a compiler, which is going to take this text and based on the rules of the C programming language and a knowledge of the piece of hardware that I want to run it on, it's going to literally turn this thing into a series of ones and zeros. And that is going to be unique and specific to the particular processor. So in this case, it's the LPC 1768. If you wanted to run this program on an Arduino, which is an 18 mega processor, it would be a different set of ones and zeros here. It might be the same code in the right, but it might be 1, 0, 0, 1, 1, 0. It's just a different pattern here. Okay, so two important pieces to take away from this slide. That the compiled code is specific to the target processor, and we'll oftentimes talk about that it's not portable. Right? Once a code has been compiled, it is linked forevermore to the particular hardware architecture of that machine. Right? And furthermore, it's the only thing this processor does. Okay, so the only code this processor is going to run is your code starting at line 1 and going through line 12. That's it, right? Incidentally, when I talked about the software downloads, all of those pieces are compiled programs. Those are ones and zeros that you're going to install, and they're specific to your target processor, which is why you have to pick the 64-bit AMD version and not maybe the version for Mac OS, right? Once code has been compiled, it is specific to a particular hardware platform. Does this make sense? Okay. All right, so let's think about this program a little bit more. So I'm running this thing, and I've got, I start it up, declare this. Pretty quickly, I drop into line 6 here. And line 6 starts my loop. So I'm going to turn the LED on, I'm going to wait, turn it on, and do this. Imagine that I had maybe a set of probes on this microcontroller that I could say pause, right? And I could inspect and say, what line are you on? You're on line 8 right now, or you're on line 9 and line 10. And I could try to do that several times. And I could ask the question, which line statistically am I most likely to be on when I pause my program? So maybe we'll take a few inputs here. Who votes for maybe line 7 or line 9? They're pretty similar, right? Do we think if you were to pause the program, how often, would you hit line 7? Pretty often, not that often? Someone's got to say something.
Pretty often, since it's just kind of cycling through 7 to 10.
Okay. Yeah, so we're still going to execute it a lot of times. We're going to execute all of these lines the same number of times, right? If I were to run this for 10 minutes, line 7 would have executed 1,000 times, line 8 would have been 1,000 times, line 9. But the question I want to ask is, how long would it have taken it for the computer to have executed line 7 here versus maybe line 8 takes longer to execute? Oh boy, my pen is failing me here. So how long, I guess it's easier to look at line 8. How long does it take the computer or the microcontroller to run line 8?
0.01 seconds.
Perfect. So 0.01 seconds. And how long does it take to run line 7?
Super fast.
Super fast. So let's think about that. The LPC runs it, has a clock rate of something like maybe 10 megahertz, say. That means that 10 million times per second it can execute an instruction. So line 7 will take a 10 millionth of a second to run. All right, that's That's pretty quick, right? So if we were to watch the time flow here, it would be line 7. Oh my gosh. I will fix my pen. But it'd be line 7 taking about this long, and then my wait would take forever, and then I would have a teeny little line 8, and then I would wait forever again. And so the vast majority of the time I'm stuck in these wait blocks. Okay? And let me just give you an idea visually on how fast these things run. I think this is kind of cool. Let me discard that. Let's switch over here, and I've got a Raspberry Pi, which is a single board computer that is pretty popular these days. I guess you can see it here. It's kind of the size of a credit card. And it's got a microprocessor on it that comes from like basically a cell phone processor. You can kind of think of it that way. So let's look at the pieces on here. And it's kind of fun to stare at circuit boards if you're a certain kind of person. And they look like little cities, right? So can you see these are the capacitors. This is actually the processor itself. It runs by transistors turning on and off quite quickly. This runs at a gigahertz, so that means at 1 billion times a second is executing an instruction. And these transistors are much smaller than you can see, but there's so many of them, and they're switching so fast, it actually produces so much heat, the thing will melt itself unless you put a heat sink on top of here. So these capacitors are needed for various operations, and if we're in a double E course, we talk much more about them. But can you see the little green tracks here that connect everything together? Right? Like right down here by the HDMI. You see that weird like S? Well, what's that about? I mean, were they just having fun with the board here? And even more up here, like this kind of little jog, right? Up and down. Yeah? You see this weird? I mean, it's kind of artistic. Anybody know why we have these kind of twists and turns on the tracks when you could just... So these are the wires. So this is actually the wires that connect the pieces of circuitry together. I guess I should say that. The way we build the circuit board is we take a piece of fiberglass, put copper down, when that's what these traces are, and then cover it all with green plastic so it doesn't short out. So all of these little light green traces you see are actually wires. So why do you think this wire takes this super weird loop here when it could just go straight here? Presumably that's, better. I don't know.
Is it to like maintain the same impedance for like a single component for the different pins?
Yeah, impedance, that's like the word that we use, but that's also the word that I was like, yeah, that means nothing to me, Like, we want to match the impedance here, and that's like, if you have an audio file, you want to have the speaker impedance match your power amp. But what is it? I mean, and I'm not going to talk about impedance, but just from a very kind of back-of-the-envelope thing, if you were running a race, say you started at this pin here, and you were running this race, and your goal is to get to this processor here, right? And this pin was actually closer. It started off closer to the processor, right? I mean, you could see this one's coming all the way from down here, and this pin's closer, right? And if we started a race, and we were both the same speed, who would get to the processor first? Probably the guy that started right here, the gal that started right at this pin, right? You start closer to your goal, you're going to get there faster. Okay? So it turns out that this computer is running so fast that we actually have to account for the speed of light across these wires, right? So light, pretty fast, right? We're going to be switching these wires up and down so fast, right, that a gigahertz signal will actually propagate down this wire, and that pulse, that one, right, might get to the processor before this one. And if I wanted to send the pattern 11001 off all these pins, I'd like for this processor to see that same pattern at the same time, right? So I actually have to account for like the speed of these electrons flowing down here, which is super, super fast, right? To basically not give one leg an unfair advantage. All right, these are called meanders. And the goal with a meander is to have the distance of the wire be matched with all of the same, kind of signals in that pair. right? Now, the impedance issue is more to the idea of why are some of them quite close together and some of them far apart, and we don't need to go there, but Davis, you are correct in that regard as well. So, I mean, it's amazing. It blows my mind, right? I mean, when you turn on a flashlight, you don't think, like, how long did that take for you to see the beam of light, right? If we turn on two flashlights, like, they're both on. So this stuff is happening so fast here, billions of times a second, your computer is making an operation. And now let's go back to that sad, well, it's not sad, it's a fine program, I suppose. But let's go back to our program and see just how bored our microcontroller must be. So can you see the full screen PowerPoint again? Maria?
Yes, sir, we can.
Okay, great. So for basically zeroth amount of time, it's at line 7, and for zero amount of time, it's at line 9, and for everything else, it's sitting here at this wait. And now a processor can't actually wait. A processor actually has to do something a billion times a second, right? There's no way to say, oh, we don't need you, go turn off, right? There are some advanced kind of sleep modes here, and we don't really discuss them. What's going to happen in this wait, very literally, is that it's going to count up, starting from 1 to 100 million in this case. If it takes a billion, to get to a second or whatever, right? It's going to say 1 plus 1 plus 1 plus 1 plus 1, and it knows how long it takes to add 1 to something because it does it in a billionth of a second, and it will add 1 and 1 and 1 and 1. I mean, what a way to waste your time, right? If you said, what is your microprocessor doing 99.99% of the time? It is adding 1 to a very large number. Like, that's kind of sad. I paid $60 for this embed, and all I'm using it for is to add 1 to a number. Okay, so my point here is that the vast majority of the time, your computer is idle and waiting on you, the slow human, to do something, or for a light to be ready to turn off. Okay, so hopefully at this point I motivated the idea of, like, well, can I do more with this particular resource? If I'm really wasting the vast majority of the time, why can't I do maybe something else during this wait? So maybe during line 4 here, when I'm doing nothing in program 1, maybe I could execute like program 2. Wouldn't that be nice, right? So here I have main 2, and this is just a different version of Blinky, right? Rather than blinking an LED, I'm just going to be writing a 1 or a 0 over to teraterm. Okay? And these things shouldn't conflict with each other. You should be able to imagine that an embed, paying $60 for this thing, should be able to blink a light and write a 1 or a 0. But we have this fundamental problem that the way we've written our program with int main and a while 1, you cannot do anything else. I mean, while 1, once you're in here, the processor's never coming out of it. Okay, so clearly we have the transistors and the time and the resources in order to execute more than one program at a time, but somehow we don't have the infrastructure in terms of our software to do it. Does it make sense? Okay, so here's another view of program 1 and program 2 where I've put, and this is a cartoon, so they aren't to scale, but where I'm actively using the processor and I really want to do something is in the solid color, and where it's really just not doing anything, it's just waiting, is in a hashed color. And you see the majority of the time it's just this hashed period. So what if I had a, and here I realize I have my first error on the slide. So this would be called the program 1 plus 2. Okay. So what I could do then is have some manager actually decide to execute code out of program 2, and then switch and execute some code from program 1, and then switch and execute some code from program 2, and then switch, and then switch, and then switch, and then switch, and then switch. And so that's exactly what an operating system does for me. An operating system is the new int main. Okay, when the processor boots up, it doesn't run your code, it runs the operating system program, that int main. And that program is a little different from what you might have programmed in the past. That it has the ability to tell the processor to jump its instruction pointer, to stop whatever it's doing and to move to a different section of code and run that for a little bit, and then switch back. And so it'll actually do this periodically, like, and we'll call this a round-robin schedule. It will just start one program for a little bit, then run another program for a little bit, and back and forth, back and forth, and back and forth. And the really awesome part of this is that you as a programmer of program 1 or program 2 don't care. You program this the same way you've always done it. You have the while 1, okay? And you think to yourself that you have the whole computer to yourself. You really don't have any knowledge of the existence of program 2, okay? And you use this idea all the time, right? And I'm going to wrap this up here. We'll pick up with this lecture tomorrow. Think to yourself, probably as you're watching this video, right? You have a processor in your laptop. Maybe it has a few cores, maybe 4 or something like that. But you probably have several tabs open, and every tab is its own program. And you might have Zoom open still if you're still in the course, right? And you probably have YouTube open. You're doing a lot at once, and it's not that each one of those programs is running on some separate processor. They're all sharing the same processor, and they're getting slices of time on it. And as long as there's plenty of idle space here so that the operating system can switch back to program 1 before it's out of this hashed area, you don't care. As a user, it seems like everything's running at once. The problem becomes when you've scheduled so many programs that you just can't get back to program 1 in time. So you said wait 0.01 here, but the operating system has switched over to program 2, and then program 3 and program 4 and program 5, and by the time it gets back to this little chunk of code, you've been there for like 3 seconds. And you probably see that if you open up like 100 tabs and you start to get this really kind of glitchy behavior where your mouse moves for a little bit and it doesn't move, and you type a key and it takes a while to show up. And that's because it takes so long for the operating system to come back around and service your program. Okay, so throughout this course, we'll be working on programs that execute in operating systems. And we'll start with Windows, and then we'll move to Linux. Tomorrow we will talk about what else, in addition to just being able to multiplex programs, what does an operating system provide us? Okay, so let's go ahead and stop there, and we'll pick back up tomorrow. Please, if you can, by tomorrow, install that software so that we can start actually trying out some code together and building some good stuff. All right, any questions? All right. Several eyeballs are still staring at the screen, so something's on there. That's good. Maria, you can let everyone go. We can just say we'll close it out here. But please email me if you have questions or concerns, and I'll see you same digital location. We'll be using the Zoom Meet for tomorrow's lab. All right. Oh, I got some chat things here. Let's make sure that's okay.
Thanks, sir.
Oh, good. All right, Davis, I see your chat. Thanks. All right. Great. Have a good day.
Sure.